Hello, and welcome to the class on algorithms, specifically as they relate to arrays. My name is John Maxwell, and we'll get right into it. So, opening up here, a typical algorithm, which is known as a solution to a problem and reusable, right? If I need to perform the action again, I can do it over and over again, and it will produce the same result because it's a solution to a problem, just what I said before. So here we have a typical problem, which is, hey, what's the maximum value in this array? And the human can see it's easily 17, but if it was with millions of entries or hundreds of thousands, you couldn't really scan it with your eyes. You'd depend on a computer to find the maximum value. So to start off with, we set an assumption that the king of the hill, the maximum value, is at position 0. If you set it equal to just 0 and the array contains only negative values, you're going to have a problem. So you, for the sake of argument, set it to the beginning index value. Or you could set it to integer.min value because almost every value is greater than the integer.min value. By the way, that's another use of the wrapper class. It has min value, max value for both integer and double and can come in handy. But having set and made the assumption that the first value is the maximum, we run through every single other value, taking them out one by one and storing them in an n and comparing n to max and saying, like, oh, are you bigger? Then what we're going to do is set max equal to that value n. So running it, we can reveal that the maximum value is 17. That'll work on any size array, and so it's an algorithm that provides a solution to finding the max value. It works just as easily with the min value, and it's a typical type of algorithm, which is going through the array and having an if statement in it to find values that match particular criteria. And that is a very common algorithm that you'll need to know. So we print this out and we move to something asking if the array is in increasing order, is increasing. And let me show you the method here. And I'll zoom up a little bit, and you can see it a little better. Is increasing, we take the array, nums, and we go through it completely. Notice that we stay 2 away from the end. Nums dot length minus 1, which gets you to the second to last value, because what we're doing here is comparing I and asking if it's greater than the one after. And if the value before it is greater than the one after it, it's not in increasing order. We can return false. And if we get all the way to the end of the comparisons, we return true after the loop is done. So it provides a mechanism for early exit. As soon as we find a condition fails, we return false. A bit more on the -1 stopping condition. When we get to the last value in the array, we don't want to go to I plus 1. That would be a mistake. We would have an array index out of bounds, and so we stay at nums.length minus 1. Be aware of that, because it may not be in the context of checking whether an array is increasing, but it may be in another context where you're using an I plus 1 or an I minus 1 index, and you will be writing the for loop so that you create an error by going out of bounds, either over the top of the array, or if it's a decreasing for loop, out through the bottom of the array to a position -1, which is not in the array. So running it, we say, wow, our initial array, 1, 5, -3, 17, 9, 10, etc., is not in increasing order. But you notice we do a sort, which is the subject of the reading this week. In this case, we'll do selection sort. Next week, we'll feature selection, insertion, and merge sort. Okay, so here we come again with recursion on merge sort. But let's explain what selection sort does. Okay, we'll look at it here and say, okay, here's the array unsorted that comes in. I put it in the comment so you can see what's going on. And we set the min, okay, what happened? Min equals 0, okay. We're just declaring a variable that we're using. And this essential part of selection sort is we compare every value versus every subsequent value. We basically repeat that. We compare every value in the array versus the remaining values to see if there's any one value after that we're comparing which is less than the value. Okay, so hey, we're going to say min, the index where the minimum value is I on line 20. And that is, we're going to say, like, the minimum value for the sake of argument is in position 0. Then what we're going to do is compare at I plus 1, okay, that value at index 0 to the next value. So first we're comparing 1 versus 5, and nope, that's not less than, and so min remains at position 0. And then at position 2, negative 3, we find, oh, yeah, this value at y is less than the minimum index. We'll just store position 2, index 2, in the minimum variable. And we'll go so on and so forth. Is negative 3 less than 6, 5, 6, 7? So what we find is that the minimum value is negative 3 stored at index 2. And then the inner loop is done. And we swap the values down here so that negative 3 goes in the first position, 5 remains in the second position, 1 is in the third or at index 2, and all the other remaining values are the same. Back up to the top of the loop, the minimum index is position 1. It doesn't find any value that's less than, oh, it does. It finds 1, which has been swapped in. And at the end of this inner loop, the swapping, it is negative 3, 1, and 5. And it goes on from there. So essentially, it will sort the array. All right. It's not very efficient comparing every element versus every subsequent element, but it does work. Okay. And it's probably not one that will be used at work to sort vast databases. But let's look at the context. Note, nums goes in and gets sorted within the array. And when we print it out, it prints out in sorted order. So there's another side feature here. When you have a reference variable like an array, and what is a reference variable? It's like an AP rectangle or an AP point or any of the reference objects that we've created, a soccer team. You know, what happens is when you make a change in a function like that to the values, then they stick in all contexts, in the context of main and in the context of selection sort. What you can't do is dereference nums by saying nums equal another array, nums2. That will not stick. Okay, so what you're doing here is passing a reference value, which is the key to the object in memory and the right to change that object. And so we ask, is it increasing order after we sort it? Yes, it is. Okay. So that's an early look at selection sort that we'll talk about again. Let's move over to insert and delete and say, hey, what we have is an array, numbers, which has five values in it. Initially, they're all 0. And we set the indices 0, 1, and 2 to 5 because when you insert particularly, you have to have space in the array. So I purposely left two values of 0 at the end in positions 3 and 4. And what we want to do is insert 13 at position 1. Okay, so here's the insertion algorithm. You start at the last index, decreasing by 1 until we reach the index position to be inserted. What we're doing is shifting the values up towards the end, provided there's space in the array. So I start at the end, which is numbers dot length minus 1, and we continue until we get to the index, because we need to move what's at the place where we want to put the value up into the following index. We decrease by 1, and we say numbers I equal numbers I minus 1. So the second to last shifts to the last, the third to last shifts to the second to last, etc., until we get down and assign the new value 13 to numbers. And so we'll run that and say, oh wow, what did we do? Line 34. Oh, wow. I don't even know how that happened. Okay, we'll run it. Okay, after 13's inserted at index 1, here it is. 5, 13, 5, 5, 0. We basically shifted all of the elements upward. Okay, so that's the way insertion works. So we're going to remove 13 again, and the algorithm is to remove, start at the index where the value is to be removed and shift the values down. In other words, cover it over. So we start at the index and then we go up until the very last index and I++. So watch how this works. I equal numbers I plus 1. So after it's removed, it returns to 55500. Okay, so the concluding question is it better to sort like at the end of the day? You know, like in the end of the business day after you added customers or sales or whatever, patients in a trial, whatever you're storing in the array. Is it better to sort them at the end of the array, or is it better to insert and remove to keep it in order? Well, that depends. We'll just ask you to think about that. But, you know, think about the array list. When you set a value at a particular index, you're overwriting that value that's currently there. And so the array list is doing this removal algorithm behind the scenes. And when you add an index, you're basically doing the insert algorithm for an array list. And so to me, it's a lot easier to use an array list, but understand that this is the basic algorithm that's going on in the background. And, you know, think of that. Think of how an array list class might look like. You can't really see the code, but this is it. Of course, there's all sorts of protections. An array list does not have a finite size, so if you want to insert a value in an array list that's air quotes completed already or filled, then you'd have to add elements, and that's another thing. The array list is probably built on a primitive array and performs these operations in the background. Just something to consider when you appreciate an array list and use it. Well, this has been a discussion of algorithms. Reach out during this week if you have any questions.